the following. So the one protocol is very easy. It's like QKD. It's basically exactly the same. So Alice distributes this continuous variable EPR pairs, then both measure randomly either in the X or the P quadrature, and then generate the data. So after they executed the protocol, they're waiting a time delta t. This is basically time a malicious party has to store the signals if he wants to attack this protocol. Before the property, I'll just follow directly from the properties of the state of this EPR state. And these are that if both measure in the same basis here, then the outcome are perfectly or strongly correlated. In the other case, they're not correlated. And moreover, what's important, they don't know in which rounds they have or they have the same basis. So now we can use that to generate oblivious transfer by only doing classical post-processing. And this is the protocol here. So in the protocol first, Alice sends the basis choice to Bob. Bob then checks in which rounds they have chosen the same basis, puts it in this index set here, I of t, and t being the choice bit. That's important. And then he's also forming the index set, the one of the basis of the signals in which they have chosen different bases. Then he sends Bob to Alice. Alice forms the corresponding substrings. For each substring, she's using a two-universal hash function and just hashes the string, the strings here to L-bit strings. So then Alice is computing error correction. This is very important for continuous variable. We have strongly correlated data, but that's perfectly correlated, so we have to send some error correction. So she's just sending error correction for both substrings to Bob. Bob now knows that C of t, so the error correction to V of t here, corresponds actually to the strings that are correlated. He can use it, correct his outcomes, and then also apply the hash function. Alice also sends the hash function, and then gets the string out. So this is the protocol. So, and correctness just follows, because Alice can actually, given this error correction works, then these two strings C of t and C tilde of t are basically typically the same, and then the outcomes will be the same. Security for Bob is also very easy, because he only sends these two index sets, and they're completely uncorrelated to his choice bit. So this is also simple. But different is the security for Alice, because of course if Bob has a perfect quantum memory, he can just store all the signals until he receives the basis choice from Alice, and then measure according to this basis choice, and then get both of the strings. So this doesn't work if Bob has a perfect quantum memory. But now what happens if the quantum memory is not perfect? And we're going to model the quantum memory as follows. So Bob has actually here an encoding operation where he encodes all the information or all the signals into a quantum memory here denoted by L. And we assume that the fraction of quantum memories, n is the number of signals dealt by Alice, is this nu here. So here he just encodes it into the quantum memory, has to wait for this time delta t until he gets the measurement choice from Alice. So in the following, we make a distinction about the power of this malicious party by looking once at encoding strategies that are not restricted, so that we don't have further assumptions. In the second part, we look at if this encoding is a mixture of Gaussian channels. And in another restriction, we look at if this encoding is only independent and identical on each signal, or at least very, very small numbers of signals. So this is basically the memory attack Bob can do. And because I don't have so much time, I just rush through to the result here. And for the result, in order to understand them, I have to introduce two things. Of course, the power or how much, the security of this protocol has to depend on certain things of the malicious party's quantum memory. And here, the crucial quantity is this classical strong converse capacity. So what this capacity is a capacity is a rate above which, if you want to send classical information through this channel, your success probability to do this reliably will decay exponentially. So we need this exponential decay that you actually can encode information classically. So this is the strong converse capacity. So then we need another thing which I call uncertainty rate. And the uncertainty rate basically tells me how much uncertainty Alice can create by doing her measurement. So this is the picture. So we assume basically that Bob can send Alice an arbitrary state, and Alice is just doing the measurement either in X and P and gets the outcomes. And we're asking here the measure, the important measure is this moving entropy, and we ask how much entropy we can generate by this kind of in this situation. So these are the two quantities that are going to be important. And then what we show is that security can be achieved if the following holds. So we have here this uncertainty rate I just explained before, and then this uncertainty rate minus the error correction rate. So the error correction information Alice has to send to Bob during the classical post-processing. So one half of this kind of difference here has to be bigger than, I call it like the effective classical strong converse capacity. I just multiply with kind of the number or the fraction of quantum channels the malicious party has times this classical strong converse capacity. So if this is satisfied, then we get security. And the length of the bit string in this oblivious transfer is given by this formula here. Okay, but now we of course have to quantify this uncertainty rate in order to say something for which kind of memory and which memory bounds we can actually get security. And for that we derive three uncertainty relations. So relations of this form here, so we interested in this quantity lambda. And the first one is no assumption. So this plot is like shown depending on the discretization of my homodynamic. So this is the red line here. So this one is with no assumption. So then we show about on the Gaussian assumptions. These are Gaussian in this memory attack model. These are Gaussian encodings. This is this blue line here. And then we show about for these like individual and independent encodings. This is translated in this picture. These are product states. And this is this green line which unfortunately just overlaps with the blue line. So, but what we saw in the previous slide is that the error correction rate has, or like the uncertainty rate minus the error correction rate has to be at least larger than 0, meaning that these bounds here have to be above this yellow line. So this is the error correction rate I plotted here for this parameter here. So for highly squeezed state here, but So we see that, for instance, if we don't have any further assumption, we only have a small region of discretizations in this discretization parameter where we observe this error correction vector. So we can get security without kind of assumption at the moment, but we have to assume very bad memories. Okay, so let me come to my last part and look at a certain model for this memory, for a malicious parties memory. And we look just at the loss channel with transmissivity tau and some noise, some additive Gaussian noise with a variance. So for this channel we know this classical strong converse capacity, so we can actually analyze the security. So, and this is what we find. So here we plot, here is the noise variance. So this all plots in h bar equal to 2. So and this is the transmissivity. So and this is the fraction of quantum channel malicious party has. So if we know that the fraction it's around like 1/10 of the signals used of the parties, then we see that we actually go very fast to like transmissivity that are very high. So we have to have for the malicious party has to have a very good memory. So this is plotted for this kind of like parameters here. Okay, let me quickly summarize the results. So I showed you a protocol for optical continuous variable implementation for oblivious transfer. We also have a protocol and a security analysis for bit commitment that's actually even simpler because it doesn't use error correction. So we showed security, and basically the take-home message is that we have a high uncertainty rate, a low error correction rate, and this has to be bigger than this effective classical capacity. So we also showed some new uncertainty relations. We actually learned that they are very difficult, the one we were looking at, and there's still some open questions. So we saw that we don't have a good uncertainty relation due to, I believe, only technical reasons that we cannot get better security without further assumptions. Okay, and another open problem actually, at the moment we reduce it to the classical capacity, but of course it's kind of away from the actual problem, so we want to actually relate it to the quantum capacity of the channel. So, thank you for your attention.
Thank you. So we have time for one quick question. You said that you have composable security. Which flavor do you mean? Like sequential, parallel, universal?
Oh, that is actually universal. You can concatenate this in an arbitrary.
And how do you get around the problem that the simulators and quantum memory can be used to break the other instances?
Maybe we can ask Stephanie there. She's the composable security.
Sequential.
Sequential.